the introduction for Dr. Tu, and it's really my pleasure to join the first SRE LCSA webinar on the data algorithms and tools for LCA. So I found that this topic is very important and also interesting. And today I'd like to share one of our recent work, which is also collaborate with Dr. Tu. The title is Data-Centric Investigation on the Challenges of Machine Learning Methods for Bridging Life Cycle Inventory Data Gaps. So I prepare to use this this is a case study. So I prepare to use this case study to discuss some common issues we may face during applying various machine learning models in filling the data gaps in the lifecycle inventory, and what we could do to partially solve these problems. So as I believe, as you all know, the lifecycle assessment, the LCA, is a widely applied tool to assess the environmental impact of a product or services during its entire life cycle. So this means in order to conduct a lifecycle assessment of a specific product, so we need to track the potential environmental impact from its cradle to grave, starting from the raw material extractions, then the manufacturing phase, distribution phase, use phase, and final waste disposal. So in order to conduct an accurate LCA study, we need to collect the data for all these different stages. So you can see that a good LCA study is highly data intensive. And in a standard LCA workflow, one of the most important steps is to conduct the life cycle inventory analysis, the LCI analysis. So this step constructs an inventory of input and output flow for product, including the energy and the material exchanges, and also those environmental emissions in the product life cycle. So for example, here we'll give a very simple example. So for a unit process to produce 1 kilogram of plastic film, so we need 1.02 kilogram of polyethylene and 0.68 kilowatt hour of electricity, and generating about 27 liters of wastewater. So the LCI is the recipe for a specific production process, and a comprehensive LCI is the foundation for a successful LCA study. However, the collection of data in the LCA study is often a major challenge. Traditionally, the data collection methods include those on-site investigation of manufacturing process and the laboratory tests, which are quite time-consuming and also expensive to collect those first-hand data. And we can also try to collect some LCA data through surveys or questionnaires to the industry companies, but due to some confidentiality concerns, not all the data could be collected in this way. And we also could collect some second-hand data from the existing database or through the published papers, but this data may not always suit your specific cases. So therefore, the LCA studies are always challenged by the data availability and the data quality issues. And this may limit the application of LCA to support the decision-making. So, however, this the challenges are a little bit hard to be solved by using the traditional methods. And it's urgent for us to find some more efficient method to fill the current data gap. Recently, with the rapid development of AI, has opened up some new possibilities to solve the data gaps in LCA studies. And one typical technique of AI is the machine learning. Machine learning is, already has shown remarkable performance across diverse domains, allowing for their applications to extract some patterns and also some insights from very complex data sets that might be a little bit challenging for our human beings. Accordingly, an increasing number of studies have tried to apply the machine learning methods using this data-driven tools to estimate the missing inventory data in the LCA. And the results have demonstrated in multiple papers have shown that the incredible potential of these methods to solve the data bottleneck issues. However, most of these current efforts primarily only focus on demonstrating show some preliminary results, such as showing the efficacies of the proposed methods by comparing the proposed model, by using different algorithms. We just compare the performance between the various algorithms or compare with some other baseline models. Meanwhile, the efficacy of this method is highly varying in different studies, which can be affected by the composition of the training data, the extent of the missing information, and some other factors. So this means the model may only be applicable in their own cases and cannot be implemented to other studies. So this may kind of like the limits the trustworthy and also the generalizability of the models. So there is a need to explore the reasons really behind the varying performance of different machine learning models in different studies and provide some more generalized insight for future studies. So in this study, we try to do a kind of like the not that typically, we try to conduct a data-centric investigation to discuss several fundamental challenges observed from training a typical machine learning framework for estimating the missing inventory data. Specifically, we focus on analyzing the complexity and the limitation inherent in the LCSA database itself, and also during the modeling pipeline, and discuss how these factors would influence the applications and performance of the machine learning models. So in this study, we a similarity-based link prediction model, which we proposed in our previous study, was used as a reference baseline model to estimate the missing unit process data using limited available information. And a very important reason for selecting this machine learning model is because like the simpler version of this method is the so-called proxy method, has been actually widely used in the relevant LCA studies to estimate the current missing data. So that is a very straightforward and very powerful tool. The intuition of this method is also quite straightforward. So we simply assume like the similar processes should also have similar flows. Thus, for a new unit process, if the knowing part of this unit process is sufficient enough, we can use this partial information to help us to find some similar processes in our database. And then we'll use the information of these similar processes to help predict the missing part. This procedure is quite similar to the friend recommendation systems in the social media like the Facebook. So if two people have many common friends, the algorithm could identify the potential but unlinked friends and makes recommendations. So the similarity-based methods have two steps. So the first step is simply to calculate the similarity between the each process. We use the Minkowski distance to evaluate the distance between the different unit processes based on their knowing part information. And then we calculate the similarity by using the inverse of their distance. And after that, we estimate the missing data using the so-called k nearest neighbors method, the KN method. So this means for each missing flow, we will calculate the weighted mean of the k most similar processes to get the estimations for the missing part. So in this study, we evaluate the baseline model performance on the widely adopted eco-invent UPR unit process database, the UPR database, and the situation with about 5% of the data missing. Based on the grid search methods, so the optimal hyperparameters were found to be the Q equals to 0.075 and K equals to 2. And specifically, the distance parameter Q is quite small. You can maybe have already noticed here. So with such a very small Q, the distance measure becomes extremely sensitive to the small difference between the different processes, which could help us to find the trivial difference in the normalized the data side. Meanwhile, the small value of K demonstrates that by only utilizing the information from just a very few most similar processes is sufficient enough to provide a reasonable estimation for the target processes. For the prediction of the non-zero missing flows, the overall model performance could achieve a mean absolute percentage level of around about 35% during the leave-one-out cross-validation. So this results indicating that our model can provide an ideal and also robust performance to estimate the missing lifecycle inventory data. Although this baseline model demonstrates great potential and also for estimating those kind of missing data, there are still some challenges that we have faced during the model training and the modeling framework. This kind of challenge is first from the unique structure of the UPR dataset. We have taken a look at what is the kind of like the flow appearance and process appearance like in the original UPR dataset. We can see here, so the UPR dataset, because only includes the on-site energy and resource use and emission data for each process. So this means most interest in the UPR matrix are actually zeros. Only certain flows have like physical meanings. This means like the eco-event UPR database is can be considered as a very sparse matrix, with only about like 0.5% of the entries are non-zero. So this means for a typical process, any missing of these non-zero flows will result in significant information loss. So every piece of information is important to us. And in the same time, the sparsity often leads to some imbalanced data set, where some classes or categories are underrepresented. Here we have did a statistic, like so you can see here, the top 20% of the flows with the highest appearance could account for 72% of the total non-zero flows. And these dominant flows, which you can see on the upper left, are some like the very basic flows, such as like the water emissions, electricity usage, are some very basic flows that almost exist for every process. Besides, for the different processes, the number of like the unit processes under each ISIC classification could also vary significantly. Here we see like the number of unit processes under each ISIC classification could vary from like the 1,000 like the processes to a single processes. So this sparsity and imbalance issue can lead to some biased prediction and a poor model performance for those like minority classes. And in addition, the data magnitude and the normalization is another issue need to be considered. Unlike the traditional matrix, the UPR database has a very clear physical and chemical meaning. It represents like the energy or emission flows in the different unit process. So considering the different unit of processes or flows, and their inherent difference in their industrial activities. So the order of magnitude of the different elements, the value in the database may vary greatly. And in our original UPR database without pre-processing, the largest value can reach a number of around like 1.7 times 10 to the power of 11. And the smallest non-zero value is only about like 2.5 times the 10 to the power of negative 14. So this kind of huge difference of the varying orders of magnitude may naturally assign higher weights to those kind of larger values and skew the performance of the trained model. Sometimes we will do the normalization to alleviate this issue and prevent the features with like the larger values to in dominating the learning process. Additionally, this process could also eliminate the effects for the different unit selection during the distance calculation. For example, like in our unit UPR data set, for a single process, the units change from the kilogram to gram. The value will change, but their physical meaning actually will not change. So by using the normalization, we can kind of eliminate the effect of the varying like unit selection. However, this process may also have some disadvantage. This process may obscure the physical meaning of the data size, because like our data will have the physical meaning, like each value is represented for each unit process, how much emission could be generated. But like after normalization, the normalized data will lose this kind of physical meaning. And this time makes the distance calculation hard to interpret. So in that case, we have to consider the kind of the trade-offs like between whether to maintain this kind of physical meaning or doing the needed mathematical operation. And in addition to the issue with the data itself, there are also some certain issues which directly relate to the model development. The first issue we need to consider for almost all the machine learning workflows is the variation of model performance due to the randomness of the train test data splits. And when we use random seeds to split the data size into different training and test sites, the performance of the model can vary. So to show this point, we randomly split the UPR database into like 20 different combinations of training size and test size by using 20 different seeds. And as shown in the left figure, so the optimal model structure could vary with different optimal hyperparameter skew. And the final model performance can also highly vary on the test side. And meanwhile, even when we fix the training side and also fix the optimal model hyperparameters, the model performance still could vary when facing different test side. As shown in the right figure, when we use a different subsite for the test side to show the model performance, so the best case scenarios was about like 26% better than that of the worst case. So this means that for different runs of the same experiment, individual cases may not be a good representation of the overall model performance, leading to either overly optimistic or pessimistic like the estimations. And besides, we also conduct like several experiments to explore the impact of the data imbalance on the prediction results. So as shown in the left figure, the frequencies of the flows had a positive impact on the model performance. So this means that the flow with a higher appearance frequencies tend to have a lower like the prediction error on the their like the estimations. So this trend can be attributed to the fact that like for those flows with a higher appearance frequencies, it's easier for us to find the processes with like the similar flows as the references. However, like for those flows rarely found in any process, so the model have like the zero experiences about like their relationships. So the model structure to discern patterns and find like similar process for the comparison. So this scarcity of like the relevance reference data sets makes it challenging for the model to accurately predict the value for those kind of infrequent flows. Regarding the data magnitude issues, but on the right hand side, we didn't find a clear relationship so far between the magnitude of the flow and like this prediction error. Also, to test the generalizability of the model, we also applied our modeling framework to another widely used UPR database, the so-called like the United States Life Cycle Inventory USLCI database. Compared with the 𝐂𝐿CI, the USLCI only provides some national UPR information with fewer flows and process information, and it's about like 20 times smaller than the 𝐂𝐿CI regarding the size. And we trained and tested the model on the USLCI dataset using the exact same like the modeling pipeline. And as shown in the heat map, like the similarity-based link prediction model has worse modeling performance compared with the results based on the 𝐂𝐿CI. And the prediction error is about like 46% higher than that for the 𝐂𝐿CI. The reason for such difference, it was mainly due to the difference in the like size for these two databases. In the USLCI, the limited number of processes make it very challenging for the model to consistently find those truly similar processes. And this limited candidate pool potentially compromise the model's performance. So this is all the findings we have in this study so far. So this study is kind of like, maybe you have already noticed that it's not a typical study we usually see. Instead of like providing some direct conclusions, we raised and discuss some questions and concerns when we will face during the modeling framework for like using different machine learning applications in LCA studies. So despite several limitations for the data-driven solutions for the LCI have been identified in this study, we still like foresee great opportunities and potentials and aim to provide some suggestions for the future research. And this is actually our target for this study. First, similar to our method, although we only use one single method in our current study, other existing machine learning models also tend to use the information from a single database for the model training. So as we have witnessed the data imbalance issues and also the size issues for a single database, thus the data integration from multiple sources to obtain a larger data set should be promoted and encouraged in future studies to address the potential data issues. And for the second insight is that when presenting model performance, it's important for us to acknowledge that there is some randomness of the results. Reporting performance matrix by using some average and also providing the confidence interval can help to convey the reliability of the results. And techniques such as the cross-validation can also be used to provide a more robust evaluation of the model performance. Meanwhile, as any changes in the model training process could influence the final model performance, so there's a needed call for the application of the FAIR principles to all of the machine learning applications in this field. So the researchers should provide their source code and also enhance their documentations of the methods to facilitate the producibility and reusability of the results. And moreover, when handling the data sets like the UPR dataset, it is crucial to balance maintaining the physical meaning of the data with the application of necessary mathematical transformations. For example, for most of the machine learning applications, the normalization is a necessary step. However, considering the special characteristic of the UPR dataset, we cannot simply treat the datasets from a purely mathematical perspective. Sometimes using the data in its original format with clear physical meaning may provide some additional insights. So this is kind of my final page. Currently, we have already started the efforts to build a more robust data infrastructures for the LCA studies. Currently, we have started the Qiangong initiative, which is led by Professor Ming Xu from the Tsinghua University. We have already kind of collaborated with 43 university and research institutes, and is working on constructing an open and transparent LCA platform. And we hope this kind of efforts can further encourage the adoption of more advanced data-driven methods in future LCA studies. So before concluding my presentation, I would like to also express my gratitude to my co-authors and the participants of all this work. So that's all for my today's talk, and thanks for your listening, and welcome for all the questions.